Okay, so now I just want to do a visual example of calculating some of those quantities we talked about in the last video. And we're going to do the same problem a couple different ways and add a few things just to show that each way of calculating is equivalent. So what I want to do, we have a position vector here. So this is just a position vector, and this graph is a screen grab from Desmos, great resource. And this is the graph of this position function. And I've labeled the y-axis ry just to kind of get used to the r. So that's the the position on the y-axis, or our vertical position, and down here on the x-axis is our x position, or our horizontal position. So what I want is to find the change in position vector, or the displacement vector, from time equal to 2 to time equal to 3. So the first way I want to do it is just to get it directly. It's just to figure out where we are at 2, where we are at 3, and what we had to do to move from one to the other. So my displacement vector at time equal to 2, so at r of 2, we have 2 cubed, which is 8. So this is 8 I hat plus, and 2 times 2 is 4, times another 2 is 8 as well. So this is going to be 8 j hat. So our position vector at 2 is going to be 8 in the horizontal plus 8 in the vertical. So let's go ahead and get that. If we start from the origin, we're going to go 8 in the horizontal, and then from here, we're going to go 8 in the vertical. And our position vector is the, oops, don't want that. Position vector is just this vector right here. So that is our position vector. And actually, we can make this, we'll make that red. So the red vector is our position vector. All right, so from R2, we move to 3, to our position at 3. 3 cubed is going to give us 27, so that's 27 I hat. 3 squared is 9, times 2 is 18, so this is 18 j hat. So we go 27 in the horizontal, and then we go up 18 in the vertical, and that lands us right exactly there. And our position vector there, we can give by this line right here. And so we want our change in position from 2 to 3. So we started right here and we ended right here. What's our displacement vector? And so we just take the vector that starts at 2 and goes to 3. So actually, let's do that in a different color. Let's do that in green. So this green vector is our displacement vector. So this is our displacement vector. So what I want to do is just take that and move it down here. We're going to compare the vector we get from the other methods. So this is our displacement. Notice we didn't calculate the actual values for this displacement. All we calculated was the kind of visual geometric point of view from it. So we didn't actually get the values. We'll do that in a minute. All right, so we got it that way. Let's get it in another way. We said the displacement vector, so let's go down here and start fresh. We said the displacement vector, or the change in a vector, so delta r, that's going to be, if we're starting at 2 and going to 3, well then the displacement vector is r of 3 minus r of 2. That's our change. So we talked about how to subtract vectors in the last video. Excuse me. So let's just get the visual vectors again and subtract them and see what we get. So r of 3, we said, was at the point, let's go back up here and check. R of 3 was here at 27, 18. So if we start here, we go to 27, 18, gets us right there. And then R of 2, I believe, was at 8, 8. So let's go to 8, 8. So right there is our position vector. And we want to subtract. We want R3 minus R2. And we said the way we subtract, was to take the second one and reverse its direction. It's just like adding the negative vector. So we want to reverse the direction, and then we want to put it on the tail of the last one. Oh, I lost my little arrow there. So this is where we end up when we subtract. So let's get our position vector, or our displacement vector, there. So the solution, R3 minus R2, should be this vector right here. And that should be the same vector that we got from the last one. So we talked about how vectors are just information. We can move them around and it doesn't change their meaning. So let's take this one right here, copy it, and let's see if it's the same vector as what we got earlier. And it is. It is the exact same length as the one we got earlier. So those two ways of getting this displacement vector are identical. So let's do one more. Let's do it purely mathematically. We want to just subtract and actually get the values out of these vectors. So let's take R3, which we said was 27i hat plus 18j hat, and then R2, that is, what was R2? R2 was 8i hat, or R of 2, I should say, plus 8j hat. And then let's subtract them mathematically. So R of 3 minus R of 2. When we subtract or add vectors, we just do it component-wise. So we'll subtract the I hat components first. So 27 minus 8 gives us 19. So 19 I hat. And then 18 minus 8j hat gives us 10j hat. So our displacement vector should be the vector 19i hat plus 10j hat. That's our displacement vector. So let's draw that one in green. So we have to go 19, we'll do blue. So we have to go 19 in the horizontal, 19 in the horizontal, and then 10 in the vertical. So that's going to land us right about there. And so this should be, and I'll draw my arrows here. So the vector from the origin up to here should be, again, the displacement vector. Well, let's see. If we take this, and I'll label it, this should be our displacement vector. So if we take this one, and we copy it, and we bring it up here with our other two, it again is the exact same length as both of these vectors here. It's the same vector. So we can get that in 3 different ways. And so now what I want to do is actually calculate the magnitude of this displacement vector. The magnitude. So let's go down here to our last example. We actually have the components here. We have the components of our displacement vector, and they are 19i hat plus 10j hat. And notice what that forms here is just this right triangle. We went 19 horizontally, 10 vertically, and we have this right triangle right here. And so we know this piece is 19 units long, this piece is 10 units long. Well, the magnitude of our displacement vector is just going to be the length of the vector right here, which is the hypotenuse of this right triangle. So we can use the Pythagorean theorem to find the magnitude of this displacement vector. So we'll write it down here. The magnitude of our displacement vector, this is how we're going to get it. It should be true that 19 squared plus 10 squared equals the hypotenuse squared, or the magnitude of our displacement vector squared. So when we calculate this, we get the magnitude of our displacement vector. It's going to be the square root of 19 squared plus 10 squared. And if we type that into a calculator, we get about 21.47. 21.47. And maybe we were in meters, and whatever unit this is, we'll say it was meters. So the length of this vector right here is 21.47 meters long. So that's some visual examples of this displacement vector and what it means to calculate that. In the next video, we'll just continue with this same setup here, and we'll find the instantaneous velocity and the average velocity and some information about acceleration as well.